setting up his trees in different rectangular arrays. He's got 36 trees. So there's, he can make it a 6x6 array. He can make it a 4x9 array. He can make it a 2x18 array. He can make it 1x36. You with me? There's a whole bunch of different ways Mr. Arboretum can set up his 36 trees. That's what they're asking us for. In the end, they're really saying, what are all the numbers that go into 36? That's what you're supposed to find. Does that make sense? Here's the original question. He's planting fruit trees in a rectangular array. What are, find for each of the following, what are the number of rows? It goes off the screen a little bit there. But anyway, yeah, so bottom line, what are all the different ways he could do this? Now, you could try just guessing around. You might get a few of them. But it's important to be able to get them all. To get every single factor, not even missing one. Factors are divisors, right? Things that divide into the number. Don't forget 1 and 36. Those go in also, right? So remember I gave a game plan. You could just guess around, but it's going to be too hard when the numbers get big, like 196. Isn't that what we did last time? So what was the game plan? Well, it was to make a table. You make a table here. And make a table. And you start with 1, Remember how that works? And we're going to put a bunch of rows and columns. Bless you. And how do we do it? Well, we've got to break down the 36 over here first into primes, right? What's 36? You can 4 times 9, 6 times 6, whatever you want. Doesn't matter. You can go however you want. Just keep going. There it is. 36 is 2 2s and 2 3s. Tracking with me? So 36 is 2 squared times 3 squared. By the way, if you did it a different way, you'd get the same answer. I don't know if you know that. If you did 36, you started with 4 times 9. Or 2 times 18. Doesn't matter. What times what is 4? 2 and 2. What times what is 9? 3 and 3. So we got 2 2s, 2 3s. There's actually an official rule called the fundamental theorem of arithmetic, which says there's only one unique way to break down any number to its primes. It's like the DNA. It's the building block of that number. So 36 is made out of 2 2s and 2 3s. There's no other way. That is it. That's its essential identity. That's its DNA for a 36. 2 2s and 2 3s. There's no other way. If you go all the way down to primes, you can go 4 times 9, but those aren't primes, are they? So if you go all the way down to primes, however, it's always going to be that. So now, now there's a difference between finding all the primes and finding all the divisors. Are you seeing that question? If somebody just said, what are all the primes, just primes, that go into 36, I would just say 2 and 3. That's it. Those are the only primes. 4's not a prime. 9's not a prime. 6 is not a prime. Right? But they're not asking that. They're saying all factors. Not just prime factors. All factors. All numbers that go into 36. How do you find that? Well, you use the primes to find it. Basically, any combination of those primes, any way you can put those primes together, will make a number that goes into 36, because these are the building blocks of a 36. So if you use them to make something, that thing will go into 36. That's kind of the thinking. So what do? Remember how it works? Remember, you take one of the primes over here, like 2 or 3, doesn't matter, whichever. And then you start with 1, you go times 2, times 2, and you go until you reach the maximum, which is 2 squared. That is 2 squared, isn't it? 4. That's as far as we get to go. And then on the other dimension, across the top, I'm going to take the other prime. I'm going to go 1 times 3, times 3. And that's as far as I go, because 3 squared is 9. So there's my array. And then I just multiply across and down, don't I? Let me slow down for just a minute. You're getting the hang of this. So the way to find the systematic way, which is kind of overkill on a pretty easy problem like this one, but when they get really hard, it's useful. So it's basically you break down the 36 to its primes, 2 squared, 3 squared. And then you start with 1 at the top row, top column, and then you just go times 2, times 2, times 3, until you get up to the maximum, 2 squared, 3 squared. And then you just multiply all this stuff on the inside. So that means 1 times 1, 1 times 3, 1 times 9. 2 times 1, 2 times 3, 2 times 9. See what I'm doing there? I'm just taking 2 times 1, 2 times 3, 2 times 9. And then 3, or 4. 4 times 1, 4 times 3, 4 times 9. These are all the numbers that can divide into 36. Now really, we could have found that out pretty in an easier way, but this way is for sure. I'm going to list them out. You can put them in any order. It doesn't really matter. So the homework question wants you to just list them all out with commas. Any order is fine. There's what the question wants as the answer. Is that making sense? We good on finding all of them? So probably on the exam, there'll definitely be a question like this on the exam. A lot of the points will be for getting them all. Like if you get them all but just leave out 18 or something, that'll actually cost a lot of points, because that's kind of the point, is to get them all. Anybody can come up with a few random ones with a calculator in their hand. But the main point is having a system by which you, for sure, get them all. Does that make sense on that? So I really encourage you to use the systematic. I don't want you to think I'm mean ahead of time when I grade. So this, I'm going to give partial credit on the exam. But on this particular question, I would be like maybe only 1 point out of 4 if you only missed one of them, which seems harsh, huh? Like, I just missed the 18, I got 1 out of 4. Well, yeah, that's kind of the point on this one, is that you get them all. Anything less than all is kind of missing the problem. Make sense? That's why I'm giving you a system, so you for sure will get them all, because that's kind of the point, is that you can get them all. So on your own, let's make one up. Let me think. 72. All factors of 72. No, that's not a good one. It's too much like the one we just did. Sorry. 200. Is that a good one? Yeah, I like that one. All the factors of 200. Find all the numbers that go into 200. So you have to do first, break it down, find the primes. Find the prime building blocks that make that number. So I'm going to do the first step, make sure you're on track. I'm going to go 2 times 100, but you could do other things. 10 times 10, 2, 5, 2, 5. Okay, so what are the guts of a 200? 2 cubed, 5 squared. We good with that? Everybody get that part right? Those are the primes that make a 200. That's the guts of a 200. We just opened the frog in anatomy class, and there's biology class, whatever. There's the insides of the frog. That's the insides of a 200. All right, so now use that to make a big array like we're doing. Come up with all the building blocks. All right, so how do we do it? Start with 1, and then you just pick one of the primes, like the 2, and you go times 2, times 2, times 2, until you get 2 to the third is 8, huh? So that is 2 to the third. We good there? And then across the top, you take the other prime, times 5, until you get there. And you make those into rows and columns. Then you just multiply everything in the inside. So now for the inside, here we go. Times 1, times 1, times 1. Times 2, times 2, times 2. Times 4, times 4, times 4, times 8, times 8. The lower right corner is always going to be the entire number. Upper left is always going to be 1. There they are. You just list them all with commas. Those are all the numbers that divide into 200. That's every number that can go evenly into 200. Is that good? Yeah. Bless you. Did you do the 2? You can do the 2's on the top. That's totally fine. Yeah, you should have got the same. Yeah, put the 2's on the top. It would go like this. So we start with the 1. You go times 2, times 2, times. That's fine. And then times 5 here. Like that. That's totally good. And like this and like this. then you just fill in all the numbers. So 1, 2, 4, 8, 5, 10, 20, 40. What's that? 25, 50, 100, 200. This is a 40 over here. Yeah, that's good too. That's all the same numbers. You good on that? Yeah.
What if there's more than 2?
Yeah, good question. You can see the limitations. You're dialing in well. You need a third dimension, don't you? You see the problem? So if a number is made out of more primes, like if it's like 2 cubed times 5 squared times 7 squared or whatever, what do you do then? I mean, where do you put the 7? You need a third dimension. You see, with this method anyway, with this particular method, you would need, right, because down, this dimension is 1 prime, that dimension is the other. Third dimension would be coming out of the board. You need like a Rubik's Cube kind of thing. Yeah, I mean, the method has its limitations. You would, practically, what you could do, I don't think, do they give you one like that in the homework? Yeah, so they're keeping it kind of simple for this very reason. But you're right on when you're noticing it. You'd have to break each of these boxes into 3 pieces. One of them with, somehow you'd have to bring in that third dimension. So you'd have to basically bring in one that's got no 7s, 1 7, and 2 7s. In each of these boxes, you'd have to break them into three versions. So it gets, anyway, I'm glad to talk to you about that later if you want to talk more about how you would do that with more primes. They're going to give us numbers. They're going to keep it generally pretty simple. This is a technique that works really well when you just have 2 different primes on that. Good. Other questions on doing this? So I'm not going to give you 3 different primes.